Hello, this is Mr. McGovern. This is the second video in the electric fields series where I'm going to introduce you to electrical fields. So we're going to look at what an electrical field is, the fields around a proton, an electron, and between two plates, and then how to calculate an electrical field. So the definition of an electric field is it's the direction that a positive test charge will feel a force. So this is something that I want you to remember, because if you get any sort of complicated arrangement, if you know the definition, you should be able to figure out what the electric field is around this complicated arrangement. So what do I mean by the direction a positive test charge will feel a force? Say I have a proton. What I'm going to do is I want to test what the field is around that. So I bring in a little test charge, just in my mind, that little thing there is just something that I've just imagine I'm dropping in beside the proton. What will happen to it? Which way will it feel a force? Well, they're like charges. They're both positive, so they'll push away from each other, and the test charge will feel a force to the left. So that's what the field looks like at that point. And then I can do it in other places as well. I'll put the test charge over here. Which way will the test charge feel a force now? Well, they're still two positive charges. They still repel each other. The test charge is going to feel a force up to the right there. And so you can do this for every place around the proton, and you end up getting an electric field that looks like this. With a proton, the field, it goes outwards, radially outwards, from the middle of the proton. There's a couple of things here. We've got the direction, but we can also look at this electric field to tell us the strength of the electric field. And the way you do that is you look at two lines that are beside each other, and the closer the lines are, the stronger the field, and the further apart the lines are, the weaker the field. So I can look at between these two lines here. They look relatively close, so quite close to the proton is a strong electric field. But if I look at those same lines a bit further away, they're further apart. So with a proton, the field gets weaker and weaker the further out you go, because the lines get more and more spread out. So now we've got, for our electric fields, we've got direction and we've got strength, which is given by how close or how far apart the lines are. We can do the same thing for an electron. What's the electric field around an electron? It's the same definition, a positive test charge. So in my mind I say, okay, if I drop a little positive beside the electron, which way will it feel a force? These are opposites, opposite charges, so they will attract. So the positive test charge will feel a force to the right. And I can put it somewhere else, and the positive field, test charge will feel a force inwards towards that electron. And I'd go everywhere around the electron until I get an electric field that looks like this. It's the same shape electric field as a proton, except the arrows are pointing inwards. The other electric field that we come across, especially in level 2 physics, is the electric field between two metal plates. So what I mean by a plate, not like a plate that you'd bring a sandwich out on. These are just big squares of metal, and they're connected up to a battery here, so we can make one positive and negative. So in this case, remember the long side of the battery down the bottom is the positive side. The right plate, the right piece of metal will be positive, and the left piece of metal will be negative. The same rule applies. I can see if there's an electric field there, because what I'll do is I'll drop a positive test charge. My invisible, make-believe test charge, I put it in there and I say, which way is it going to feel a force? Well, it's attracted to the negatives on the left, and it's repelled from the positives on the right. It's going to feel a force towards the left. So that's the direction of the electric field. Then I'll put it somewhere else. I'll put it down here, and we find that it's going to go the same way. And you can put it in a bunch of different places between the plates, but what you find is it's always heading away from the positive plate and towards the negative plate. Now this electric field is special. It's special because if you look carefully at the lines, they have the same distance between them. Okay, there's no point, unlike the proton, where the lines get more spread out or close together. So what you've got is a uniform electric field. This means that the field is the same everywhere. This makes it easy to do calculations and experiments with, and so this is a field that we often like to ask questions about in our exams. We can also look at what the field looks like just outside of between the plates, and if you put a positive test charge down there, it repels away from the positive plate, but eventually it's going to be attracted back towards the negative, and so it's kind of a curved field around the edge, and the same at the top there. So I've seen often an exam will ask, can you draw the field between two plates? And the achieved mark is, can you get the nice uniform field using a ruler between the two plates, and then can you put the bent ones outside the two plates as well, as to the merit grade. So because this is a nice uniform field, we can work out what the field size is between the plates, and there's a formula for that. So in this case, we have E as the electric field strength. The units are volts per meter because that's what the V and the D stand for, volts and distance. V is the voltage across the plates, and D is the distance between the plates. Yeah, hopefully that was helpful for you.